In this lecture, I'm going to introduce the plane elasticity analysis. What is plane elasticity? This appears when we reduce a full three-dimensional problem into a two-dimensional analysis. And we have three different cases of plane elasticity. The first case is the plane stress analysis. What is plane stress? It's when we assume that the forces along the z directions, that is perpendicular to this plane, is assumed to be zero. Another case of plane elasticity is the plane strain analysis. And this is the case when we assume that the deformation, not the force, the deformations along these directions is zero. Another more complex case is the axisymmetric analysis. That this appears when we assume that the deformations is invariant to rotations along a certain axis, that is an axis of symmetry. This is a cylindrical symmetry. So we are going to explore these three different cases of plane elasticity. So let's come back to the linear isotropic elasticity that provides us with these stress-strain relationships. And G is the shear modulus and can be written by inverting this matrix in this way, where lambda is the Lamé constant. This is a general case of 3D deformations. Let's explore the first special case of plane elasticity, plane stress analysis. This is an example. We have a cantilever beam, rectangular beam, and we have a force acting along the beam, and we have some reaction forces at the root of the beam. And we are going to use this coordinate system. So the forces are acting on the xy plane, and we are going to assume that there is no forces in the z direction. So we also need to assume that the domain is the same if you do any cut along the z direction. So there is a uniform cross sections along z. So the cross section is along z. So it's this rectangle, the cross sections. And then we assume that the forces act only in the xy plane. So this is the diagram that represents all the components of the stress, and this is the z directions. So if the forces in z are equal to 0, so you can see here that the sigma zz is going to be 0, sigma yz is going to be 0, and sigma xz equal to 0. So all the components of sigma with one z is going to be 0. So in summary, these three components are going to be 0 because the forces are only in the xy plane. So this is the main assumption in the plane stress analysis. Under this assumption that I'm rewriting here, I can simplify this matrix that is 6 by 6. So first, let's replace these three equations into this column vector of the stress. So here I'm going to get sigma zz 0, sigma yz 0, and sigma zx equal to 0. All the zeta component of the stress are assumed to be 0. Then these equations can be reduced into these equations. How I do this? So Exx is going to be this 2 multiplied by this 1. Nothing else, because this is going to be multiplied by 0 here. Yes. So the first row is reduced by this. The second row, we are going to have these two components only. It's reduced by this one, and the third row what I'm going to get to the third row? I'm going to get E z is equal to these two multiplied by these two. So the third row give me these equations. And then I have this row that also give me a non-zero value here. So this multiplied by this that I'm writing here. So in summary, from all these components of strain, we are going to have 4 components of strain that are going to be non-zero. In particularly, you will see that the strain along the z directions is going to be different to 0. This is a particular case of plane stress analysis. The stress is in the plane, but due to the Poisson effect, the strain is going to go out of the plane. So this is the stress-strain relations in this case, and I can invert this matrix to get this matrix. So you can use either this matrix or this matrix, depending on whether you are solving stresses or strains. Just to clarify, this is a particular feature in the plane stress analysis. So the axial stress in the z directions is not necessarily 0. So you can restrict the stress in the plane, but due to the Poisson effect, the strain is going to go out of the plane. Okay, let's go to the next case of plane elasticity. That is the plane strain analysis. This appears very much in geotechnique. So the forces are acting in the plane, but the system have uniform cross sections along a certain direction set, like before. But here we are going to assume that there is no deformations in the z directions. There is some constraint that doesn't allow the material to move in these directions. So this is going to be the plane strain analysis. So I use this as a coordinate system. Z is along the symmetry of this system. And we assume uniform cross section along Z. This is going to be the uniform cross section. Doesn't change along Z. So usually we assume that this dimension is much larger than this one, like in dams or other geotechnical structures. But the most important part is that the structure is restrained at the edges. So there is some restraint here and a restraint at the other edge. So these two conditions indicates that there is no deformations along the z directions. So this appears in retaining walls, in earth dams, embankments, etc. So the plane displacements in this plane strain analysis have two components. Displacement in x directions and displacement in y directions. And we assume that this displacement doesn't depend on z. And we also assume that the displacement in the z directions is 0. So this is the summary of the assumptions for plane strain analysis. No displacement in z. Displacement is uniform in xy plane. So let's go to the equations that we use to calculate the component of the strain in terms of the displacements. So this one is going to be 0, and these two will depend on x and y only. So let's see. So we are going to have exx is going to be different to 0 because it's the derivative ux with respect of x. This is going to be different to 0, the derivative of uy with respect of y. This one is going to be the derivative uz respect z, but uz is equal to 0, so this one is going to go. This one is going to be a combination of the derivative of this and this with respect of x and y. So this is going to stay. And this ones is going to be the derivative of ux with respect to z. That is 0 because it doesn't depend on z. And here, no, uy with respect of z. And this is going to be the derivative of uz with respect of y. That is 0 because this is 0. So this is going to be 0. And this one is going to be the derivative of ux with respect of z. That is 0 because this doesn't depend on z. And this is going to be the derivative of this one. That is 0 with respect of x. Is going to be 0. So this is going to be 0 and this is going to be 0. The other ones, they are non-zero. Okay, let's check again because this one is going to be 0. Yes. This one is going to be 0 and this 2 is going to be 0. So all the components of the strain with a set in the indexes are going to be 0. Okay, so now we go to the matrix. So this is the component of the strains that are equal to 0 by plane strain analysis. And I'm going to use this matrix and I'm going to plug this equality into the vector of the strains. So this is going to be 0, this is going to be 0, and this is going to be 0. So it's going to be look like this. And then I'm going to develop every row of these matrix equations and see which component of the strain are going to be non-zero due to these new relations. So let's see. So this one is going to be different to 0 due to these two components. Yes. This is going to be different to 0 also. Sigma z. Sigma z is going to be the lambda constant multiplied with these two. This is going to be 0. So it's going to be this one. Now first notice that in plane strain analysis, the stress is going out of the plane. Also, again, it's a Poisson effect because here is the Poisson ratio. So we are putting the strain in the plane, but due to the Poisson effect, the stress is going to go out of the plane. You can see that the other components, okay, this component is going to be non-zero, so we put this here, and these two components are going to be 0 because these two are 0. Okay, now we can replace the Lamé constant and the shear strain in terms of the Young modulus and the Poisson ratio, and this matrix can be written like this. And then we can invert this matrix, and then we can express the component of this strain in terms of the component of the stress, doing by this matrix that is nothing more than the inverse of this matrix. And we can use this matrix to solve plane strain analysis problems. The final case is axisymmetric analysis. So this happens when we have an axis of symmetry in the problem. The axis of symmetry is here the z-axis, and then if we rotate the problems with an angle theta, so we have the same cross section. So we assume that our domain is a body of revolutions, and we assume that the structure and its boundary conditions have this symmetry around the z-axis. So we use this cylindrical system. So r is the distance from the axis, theta is the angle, and theta or z is a vector along the z directions. So this is the cylindrical unit vectors, and this is the cylindrical coordinate system. If we use this system, then we can express the strain in these cylindrical coordinates. This involves a transformation from Cartesian coordinates to cylindrical coordinates, and then the strain is going to be a bit more complex. Then we assume that the displacement is invariant with respect to the z directions. What does it mean? That the displacement in r, the component r of the displacement, and z displacement, they don't depend on theta. And we are going to assume that any displacement along these directions, perpendicular to displaying the theta, the theta directions, is going to be 0. So, using these assumptions, we can replace these assumptions into these equations for the strain, and we are going to get these equations that are the 4 components of the strains that are different to 0. The other ones are going to be 0. And we are going to have a matrix, a 3 by 3 matrix with the non-zero component of the strain and non-zero component of the stress. And as in the plane strain analysis, we are going to have that we have an azimuthal stress that is different to 0. The stress along these theta directions is going to be different to 0. So the deformations along these directions theta is going to be 0, but due to the Poisson effect, the strain along these theta directions is going to be 0. So this is the third special case of plane elasticity that is called the axisymmetric analysis. So notice that the stress-strain relation is similar to the plane strain, but the strain relation between the strain and the displacement is not similar to the plane strain because we are expressing these relations in cylindrical coordinates. In summary, so we have 3 different cases of plane elasticity analysis. We have plane stress, that means that the force act on the xy plane only. It looks like this. And the stress-strain relation is this one. And we have out-of-plane deformations due to the Poisson effect. So we have plane strain, another case, that means that the displacement is in the x-plane only. That is this case. And we have the stress-strain relation that is going to be different. And we are going to have out-of-plane stress due to the Poisson effect. So here I wrote this in a slightly different way. So this is the Lamé constant. And then we have the axisymmetric case, means that the displacement is in the RZ plane only. And then I have a stress-strain relation, and I have a azimuthal stress that is different to 0. And in all these 3 cases, I can invert this matrix to have this matrix in plane stress, this matrix in plane strain, and this matrix in axisymmetric analysis. And this is the end of plane elasticity analysis.